In this lecture, we'll very briefly talk about Krylov methods for non-normal matrices. So let's start by recalling this little table that we put on the blackboard a couple times, I think, in the last few lectures. So we have covered basically 4 different classes of matrices. The left column is for solving eigenvalue problems, and the right column is for solving linear systems. And we have different methods depending on whether A is symmetric or not. And these methods, they all are based on the same pattern. So you form a Krylov subspace given some starting vector B. So B is a given starting vector. And then you form the Krylov space like this. You form an orthonormal basis to it. And then you restrict the matrix. So you express the matrix A in this basis, that's H, and then we can factorize A as follows. And we proved that when you do this, H will always be almost upper triangular, in the sense that there's one subdiagonal that may be non-zero. And if A is symmetric, then H is in fact tridiagonal, which is very nice. And generally, these methods, they work particularly well when A is symmetric, because if we look at the Krylov space here, so we see that all the vectors are drawn from the column space of A. And if A is symmetric, then that's not a problem, because the column space and the row space are exactly the same. So this basis you're building, it's going to be a good basis for the column space and also a good basis for the row space. If A is not symmetric, then that's not really true. And we've seen that there are cases where A is diagonalizable, which is sort of, in some sense, close to being normal. So normal is really the property that's very nice when you have the same set of eigenvectors for the row and the column space, or the same set of optimal basis vectors. I should express that a little bit more precisely. But so you have normal matrices, and then you go to diagonalizable matrices, which is a larger class. But then there's no longer a guarantee that a good basis for the column space is necessarily a good basis for the row space. And in general, for a general matrix, there's no statement at all that the column and the row spaces may be completely unrelated. And in that case, your Krylov space is only going to capture the essence of the column space, really. So you can only do so much. You cannot use this for computing, say, a singular value decomposition of A, where you really need detailed information about the row space. And we see this also in that the convergence analysis, it's very precise for Landschoffs and for conjugate gradients. And for Arnoldi and GMRS, there's more hand-waving, and it sometimes works and it sometimes does not. So let's just talk a little bit about some things you can do for matrices for which the column and the row spaces are not particularly related. So say we want to solve a linear system. So consider AX equal to B for a matrix where A is not necessarily equal to its adjoint, or say it's not. Then what do? So you should then have, so we want to solve this system. We have at our disposal a very fast solver, a very efficient solver for symmetric matrices, and in particular for positive definite symmetric matrices. So then the natural thing to do is to multiply the equation by a star on both sides. So you form the following equation. So this is known as the normal equation. And now notice that the coefficient matrix here, it's very nice. This is symmetric, and it's at least semi-definite. Or let's call it non-negative. And in fact, if A is non-singular, then it is positive definite, in fact. So this is symmetric, positive, definite. Which means that you can apply conjugate gradients to solve this, and this sometimes works quite well. But there is one catch, and it is, so CG can be used to solve the normal equations. And notice that this actually works even when A is rectangular. If it's an overdetermined least squares problem, as long as it's full rank, this method will work very well for that case as well. But there is a catch, and it is the following. And it's that the condition number of A star A is equal to the square of the condition number of A. And this is quite clear, right? Because say you have a singular value decomposition of A, then A star A is equal to VD square V star. So we've basically squared all the singular values. So the ratio between the largest and the smallest singular value now got squared. And this is unfortunate because number of iterations required in conjugate gradients, let's recall number of iterations of CG to reach precision epsilon. This scales as root of the condition number times log 1 over epsilon. So now if we square the, so for the normal equations, you basically lose the root. So in forming normal equations, we may square the number of iterations. So by forming normal equations, we may square the number of iterations. And if you think of, say, kappa being, say, 10,000, then for the original, we're talking about 100 iterations versus 10,000 iterations, which is quite a lot. Notice, though, that this estimate based on the condition number, it's really a worst case scenario. So things may be fine. In one case that we talked about a lot, which is when the singular values or the eigenvalues are clustered, may be better than the number of iterations scaling as kappa bound may indicate. So if A star A has clustered evals, then fast convergence. And to take an extreme example, so this is not by any stretch typical, but just to illustrate the concept, so take a matrix that the circulant matrix. So the matrix that has, so it's basically a diagonal matrix, but the diagonal is shifted up one step, and then at the bottom row you put in a 1. Like that. Then the eigenvalues of lambda are the roots of unity. If this is m by m, and there are m distinct eigenvalues, so if you try to solve ax equal to b for this matrix, then Arnaldo will basically not converge at all because the eigenvalues are not clustered in any sense. But A star A, in this case, is identity. So conjugate gradients would converge in one iteration. I mean, this is very extreme. Of course, if you have a matrix like that, then you just apply its adjoint, and that's the inverse. But in general, more generally, you often have matrices for which A star A may have clustered eigenvalues, even though the eigenvalues of A are quite spread out. So the normal equations approach is certainly feasible in certain cases. You always have to worry about round-off errors, however, that can cause problems. So next, let's consider a spectral decomposition problem. So let A be a general matrix. We don't even need to ask for it to be square. It can be a rectangular matrix. We want to compute its singular values and its singular vectors. And in this case, clearly a Krylov method doesn't work, even if the matrix is squared. In principle, Arnoldi would work. You could use Arnoldi to try to compute the eigenvalues, but in general, there's no connection between the eigenvectors and the singular vectors, or no connection is too strong, but they're not the same for a non-normal matrix. And moreover, unless there's some connection between, some relationship between the column and the row space of A, then it's just not going to work very well. So generally, we do need to be able to apply A star to get information about the row space. So it's basically a necessary assumption in order to find the right singular vectors. So let's assume that we can do that and think about how can we make the techniques that we've already developed made to bear on this problem. And the idea is to form a matrix B. That looks like this. Or one idea. There are different ways of doing this. But one set of ideas is to form a larger matrix like this. So the size of B is m plus n times m plus n. So if A is square, then B is, of course, twice the size. Like this. Okay, so now A is symmetric. So we can expect that Lanczos will work well. So we apply Lanczos, we find some approximate eigenvectors and eigenvalues, and how does that help us? So let's say that we have an eigenvector and an eigenvalue of B. So say B times the vector xy is equal to lambda times the vector xy. Then this is the same as saying, well, the top row of that equation just says A star y is equal to lambda x, and let's see, how does this work out? Ax is equal to lambda y. Okay, that doesn't look very auspicious. These are not eigenvectors of A. But if we do the same trick, we sort of form normal equations here. So we multiply the top equation by A star, we find A star, or the top equation we should multiply by A. So A star y is equal to lambda times ax, and then if we use the bottom equation, we see that that is equal to lambda square y. All right, so y is an eigenvector of a star with eigenvalue lambda squared, and conversely, if we do A star A applied to x, then that is lambda A star y, that's lambda squared x. So, in other words, so the root of lambda squared is a singular value. So root lambda squared is an s value, a singular value of A with singular vectors x and y. And notice that these actually come in pairs. So let's apply B to the vector A star y and ax, then this is equal to a star a. Is that right? A star a, yes, that's right. And then I get minus a star y. And if we look at our relations up here, we see this is equal to lambda square x, that's minus lambda squared y. We do one more step of playing this game, so this is lambda a star y minus lambda ax. And now we find that this is minus lambda times minus a star y and ax. So minus lambda is an eval 2. Which is to say that all the eigenvalues of B, they're all real because B is symmetric and they all come in pairs. If you have plus lambda as an eigenvalue, then minus lambda is 1 as well. And for each pair, there's a single value corresponding to lambda squared, and that's one singular value of A. So this is one technique. But notice that this is it's more work. It has to be more work because there's more information in the matrix than there is in a symmetric matrix. But really, we've doubled the problem size, and we now have to be able to apply a star as well. So, to illustrate the next set of concepts, suppose we want to solve Ax equal to b for a general matrix A, non-singular of course, without squaring the condition number as we did when we formed the normal equations. So, if we can apply a star, then that opens up some possibilities that we did not use in deriving the Arnoldi method. So recall from Arnoldi, so in the basic Arnoldi iteration, you build a factorization A QH, Q star, where the vectors of Q are the basis vectors for the Krylov space. And we could prove that H was almost upward triangular. So, and in addition, if A is symmetric, then H is tridiagonal. So what we can do, if we can apply a star also, we can actually obtain a matrix that almost looks like that, but that has a tridiagonal thing in the middle. But what we need to sacrifice then is that we can't have A and Q star on the sides. So instead, so let me write here with Q orthogonal and H Hessenberg. So instead, we will factorize A as Vt, so T will be tridiagonal, but now on the right, we're not going to have V anymore, we're going to have V inverse with T tridiagonal. So remember that it's still going to be the case that A and T have the same spectrum because this is just a similarity transform. So now the question is, can we build T and the vectors of V in an iterative way? And the answer is yes. So we're going to build these vectors up one after another, just like we did in the Arnoldi iteration. And the idea is now, in order to simplify notation a bit, we're going to introduce a matrix W. So let W be the matrix V inverse transpose. So this is just the transpose of the inverse. Then we have A is equal to VT W star. So now you see this sort of looks like a singular value decomposition instead. So V and W are not going to be orthogonal, and T, instead of being diagonal, is going to be tridiagonal, but it's sort of conceptually the same. So it's the columns of V are the elements that form a basis for the row space of A, and the columns of V form a basis for the column space of A. So analogously to this equation, we also have A star can be written as W T star V. And what are we going to have now? So how do we set things up? So for Arnoldi, remember how did we derive Arnoldi? Well, we had the relation A is QH Q star, and this led to AQ is equal to QH. And then we looked at these columns one at a time. So instead, what we'll do is that from this equation, we get AV is equal to V times T. And we also get an equation for W, which is that A star W is equal to W times T star. So now we've got to get two chains of relations. We're going to build V column by column and W column by column. And these vectors are not going to be orthogonal, but they're going to be orthogonal pairwise to each other, so to speak. So to be precise, we have that W star times V, this is V inverse times V, is identity. So in other words, if W has columns W1, W2, and so on, and V likewise is V1, V2, and so on, then what we have is that Wi star Vj is delta ij. So it's 0 if I and j are different. And then you can build an iteration for building these. You form the tridiagonal matrix T, and then you can build solvers that are very similar conceptually to GMRS. It's just that you have now a set of bases for the column space and a set of bases for the row space. So let us look at what this works out to. So again, we're going to rely on Wikipedia, and here's how Wikipedia lists this algorithm. So here is the biconjugate gradient method. And they've expressed things a little bit differently. This does not explicitly show applying A transpose, but notice that if you look at x0 hat times A, this is really A transpose applied to x0 hat transpose, and then the whole thing transposed. So with left multiplying a vector, you can also view as applying A transpose from the left. Or applying A from the right is sort of the same as applying the transpose from the left. So this method, it does require you to be able to do both types of matrix multiplication. So notice that in each step, we apply both A and A transpose. And other than that, the steps look very, very similar to GMRS and to conjugate gradients, and so, or more to conjugate gradients, because you pick the directions. We see that the search directions are conjugates in this sense, with respect to A. But the difficulty here is that we have much, for all the other Krylov methods we've seen, there's really a statement that they don't, as long the iteration continues, as long as it doesn't break down. And if it breaks down, then that's in general great, because that means you found an exact solution, or you found an invariant subspace if you're determining eigenvectors and so on. In this case, that's no longer the case. This can break down even if you haven't converged. And if that's something that can happen exact mathematically, then what that means in practice is that you can get numbers that are very, very small. So this number, for instance, could be, there's no guarantee at all that that number is bounded away from zero in any reliable way. So this is fundamentally a fairly unstable method. there are ways to stabilize it, and there are ways to improve this in many ways, and there's a whole science of extended Krylov methods that, there's a whole menagerie of different ones, and this is still an active area of research. But we will not talk more about that. So this will conclude our discussion about non-normal matrices.